In today's functional analysis class, we are going to discuss closeness and continuity of projection. So we are going to show that the closeness and continuity of a projection can be determined by the closeness of its range space and zero space. So we state the theorem. This theorem 10.3 in your text. Let X be a normed space and P from X to X be a projection. Then P is a closed map if and only if the subspaces R of P and Z of P are closed in X. In that case, P is in fact continuous if X is a Banach space. So to prove this, let P be closed and let Yn belongs to R of P and Zn belongs to R of P. Let Yn converges to Y and Zn converges to Z in X. Then P of Yn, this is equal to Yn, since Yn belongs to R of P. This converges to Y. And P of Zn is 0. This converges to 0 in X. What we are getting is Yn converges to Y and P of Yn converges to Y. And since P is closed, this implies that P of Y equal to Y, since P is closed. So this implies Y belongs to the range space of P. Therefore, R of P is closed. Now, on the other hand, we have P of Zn converges to 0. Therefore, P of Z equal to 0 since P is closed. P of Z equal to 0 implies Z belongs to 0 space of P. We have a sequence Zn Z of P such that Zn converges to Z. Now you have Z belongs to Z of P. So this implies Z of P is closed. So one part is over, that is, if P is closed, then R of P and Z of P are closed. Now we prove the converse. So conversely, let R of P and Z of P be closed in X. We have to show that P is a closed map. Let Xn converges to X and P of Xn converges to Y in X. We have to show that P of X is equal to Y. Now since R of P is closed and P of Xn belongs to R of P, we have Y belongs to R of P. This is because P of Xn converges to Y and R of P is closed. So Y belongs to R of P. Also since Z of P is closed and Xn minus P of Xn belongs to Z of P. This is because since P of Xn minus P of Xn is P of Xn minus P square of Xn, And you know that P is a projection, so this is P of xn minus P of xn, so this is 0. So this implies xn minus P of xn belongs to set of P. And since xn converges to x and P of xn converges to y, we have xn minus P of xn converges to x minus y. And you know that set of P is closed and xn minus P of xn is a sequence in set of P. Therefore, x minus y belongs to set of P. Therefore, if you let x minus y equal to some set in set of P, implies x is equal to y plus set, where y belongs to range space of P and set belongs to 0 space of P. And you know that this expression is unique, so this implies P of x is equal to y. Therefore, P of x is equal to y. Remember that x is I of x, so that is equal to P of x plus I minus P of x, where P of x belongs to range of P and I minus P of x belongs to 0 space of P, and this is equal to, this expression is unique, y plus some z. So P of x is equal to y. That is, xn converges to x and P of xn converges to y implies P of x is equal to y. Therefore, P is a closed map. Now, if X is a Banach space and the subspaces R of P and set of P are closed, then P is closed. So, by closed graph theorem, the closed map P is continuous. So, this proves that theorem. We write a remark: if X is a linear space and Y is a subspace of X, then there exists a projection P defined on X such that R of P is equal to Y. So you can prove this proof. Let Ys be a basis for Y. Set Ys be a basis for Y. Then Ys can be extended to a basis for X. Since Y is a subspace of X, let set Ys union set T be such a basis. Let set is equal to span of set T. Then X is equal to Y plus Z and Y intersection set is singleton 0, which shows that there is a projection onto Y along Z. That is, there exists a projection P defined on X such that range space of P is equal to Y. That is, there exists a projection P defined on X such that range space of P is Y, because it is a projection onto Y. We write another remark: if X is a normed space and Y is a closed subspace of X, the question is, does there exist a closed projection defined on X such that R of P equal to Y? So by 10.3, theorem 10.3, such a projection exists if and only if there is a closed subspace Z of X such that X is equal to Y plus Z and Y intersection Z is a singleton zero. In that case, Z is called the closed complement of Y in X. That's all for today.